Hi, my name is Felix. So here I am again to teach you something about chords and harmony. What is a chord? Wikipedia defines a chord as follows. In music and music theory, a chord is a set of 3 or more different notes from a specific key that sound simultaneously. Chords constructed of 3 notes are described as triads and consist of 2 intervals. The last sentence just describes a special form of a chord with 3 notes. The notes have to be different, since 2 notes from the same instrument with the same pitch and the same location cannot be distinguished. The resulting sound would be the same as if 1 note would be played, but louder. A specific key is necessary to be able to give the chord a name. By using a key signature, we have agreed upon a music system in a specific culture. Nature does not care about music systems. In this way, when 3 birds sing 3 different notes, simultaneously, it could be a chord. The chord used for demonstration was a C major chord in root position. Time for a short exercise. Music understanding begins with listening. Listen carefully to the played notes. How many notes are played? Click the right button. Good. To be able to communicate with each other, we have agreed to a common vocabulary. Chords get names according to their attributes. Through a vocabulary, we limit the ideas to a manageable amount. Thus, our 3 birds could sing 3 notes for which no obvious chord name exists. Chords with less established names do not fit well in our understanding of music. Most common chords are tertian, as the C major chord in our introductory example. Our musical understanding is based on physical phenomena. So, let us see how our music system evolved. To illustrate how harmony came into existence, I have brought a simple string with me. Strings are used in many instruments, like the piano, the guitar, the harp, or the violin. A string has the following main attributes. 2 fixed points where the string is kept in place. A tension, here depicted as a spring, which usually is adjusted by winding one end up on a cranking handle. A mass, even though only a few grams, here depicted as a stone weight. The mass tries to keep the string swinging when pulled and relinquished. Of course, in reality, the mass is distributed all over the string. And a length, which determines with the other attributes the natural frequency or fundamental pitch of the string. The swinging of the string through the air produces a hearable sound. Since the string is elastic and fixed only at the 2 ends, the string has the freedom of form. Let me double for a moment to illustrate the first overtone, the octave. We will now tear the string symmetrically on both sides. When we let go, we hear a different sound. The frequency with which the parts of the string did swing was double the times of the fundamental. A string with only half the length has only half the mass. If the tension stays the same, then the mass will be retracted in half the time. Thus, a string with half the length swings with double the frequency of the original string. If pulled only on one side, the fundamental and the overtone will both be present at the same time. Strongly simplified and exaggerated, the sound will be like this. Normally, the overtone has much less intensity than the fundamental. For example, a guitar string can be pulled anywhere, and you will still recognize the fundamental pitch. The tendency to swing in the natural frequency is very strong. If we have the half string again, we can already tell the frequency of the swinging. It will be double of the half string or quadruple of the whole string. Symmetrically pulled, the string will vibrate with 4 bellies. Time for a math quiz. The concert pitch, or kammertone A, is defined to have a frequency of 440 Hz. Let us swing our whole string with a fundamental of 220 Hz. Then the half string will swing with 440 Hz. And the quarter string length will swing with 880 Hz. To swing with 330 Hz, how long has the string to be? Yes, correct. Since the frequency behaves reciprocal to the string length, a string with a length of 1/3 will swing with 3 times the fundamental frequency. In our case, 3 times 220 equals 660 Hz. If we double the length of the third, the frequency will be half the frequency of the third. Here, 660 divided by 2 equals 330 Hz. And no, there is no error in the drawing. 330 is not in the middle between 220 and 440. It's nearer to 440. A logarithmic scale is used to depict the frequencies. The distance from 220 to 440 Hz is an octave and is the same as the distance from 440 to 880 Hz. Don't worry if you do not understand the mathematics. The exercises will be practical, not theoretical. We need the math to explain the music scales. The freedom of form allows for other overtones. However, the more complex a form is, the less intensity it will have. Dividing the string into 3 equal parts results in a form with 3 bellies, which is a simpler form than dividing the string into 4 equal parts. Since 1/3 will produce a sound which is contained as an overtone of a part which is 2/3 long, we are only interested in the sound of the longer part, which is 2/3 long. Thus, we get the second overtone after the octave by dividing the string into 1/3 and 2/3. The next simple form is by dividing the string into 4 equal parts, as we did before. However, since 1/4 is already an overtone of our first overtone, we are now looking into a string with a length of 3/4. Similarly, we can get the next overtone, which is 4/5. Now, the next overtone used has not a ratio of 5/6. Even though less complex forms are favored, they are not allowed to be too close to an already existing form. This is because the basic sound building blocks of a scale should be distinctive enough to be easily recognized. The musicians defined a scale to have 8 notes in an octave, including the fundamental and the octave. So far we have revealed the following 5 natural ratios: the fundamental, the octave, 2/3, 3/4 and 4/5. Reveal the 3 remaining ratios of a simple just intonation scale by moving the slider. A more mathematical explanation of these ratios is that if you take the strongest overtone besides the octave, that is 2/3, as a fundamental, and take the strongest overtone of this new fundamental, that is again 2/3, then we have to calculate the new frequency as follows. In relation to the original string length, the new string has a length of 2/3 of 2/3 of the original string length, which equals 2/3 times 2/3 equals 4/9, and will swing with 495 Hz. This is 3 half times the new fundamental, or 9/4 times the original fundamental. However, this is outside our octave. Therefore, we double the length of the string to get 8/9 of the original string, which is equal to one of the ratios you discovered, 8/9. Similarly, if we take 2/3 of our 4/5 string length, we get 2/3 times 4/5 equals 8/15. And if we take 3/4 of 4/5, we get 3/4 times 4/5 equals 3/5. The beauty of taking the strongest overtones of our original overtones lies in the fact that the ratios relate to each other. Only the ratios of the 4 most dominant overtones were used to construct the scale. Okay, let us play our natural just intonation scale. Sounds good, or at least familiar, because the sounds are natural preferred sounds through physical laws. Let us relate the string to a real instrument, the guitar. Oops, the guitar's on the head, but that's okay, because the guitar strings are aligned with the upper fixation. The A string of the guitar has a fundamental of 110 Hz. So we have to adjust our sheet by dividing all frequency references by 2, which is the same as transposing all notes 1 octave lower. Did you notice that the guitar has additional frets besides the notes we found in the 8-tone natural scale? How many unused frets do you find in the first octave?